talk about E today. Okay. Base E is another way that we can do exponential functions. This is we're on page 3 of your packet. So base E. Love it. Can't get enough of it. Okay. Lots of mathematicians went into the development of E. Bernoulli, Napier, Euler, a bunch of people. They did it, and they did a lot of it in the 1600s and 1700s. Okay. Now you think, well, you probably weren't alive back in the 1600s, 1700s, but they didn't have calculators, they didn't have computers, they didn't have stuff, phones that have calculators and the interwebs and all that stuff where they could go look up stuff. They had to build this stuff by hand. Okay? So what they did is, and I like math. Okay? It's what I do. Okay? All right? But they did this. They did this thing up here. Oops, come on now. There we go. They did that thing up there. Okay? They took the limit of 1 plus 1 over x all to the x power, and they sent that to infinity. Okay? And when they sent it to infinity, they got E. Okay? Now, E, if I typed in E on a calculator, I would get out, let's see if this works now. It should work for me. If I type in E on a calculator, come on, calculator, work for me. E to the first power, I get 2.71828, which really, I mean, that's just what my calculator is rounding to. So really it's that, and it goes on, it's kind of like pi. It's one of those that goes on forever and ever and ever and ever, and they still haven't found if it repeats yet or not. Okay? So we commonly use E as 2.71828. Okay? If you remember it, 1828, 1828, 459. Okay? But you don't have to remember that 459 part. Okay? So they found that that limit was, put it right about there. Nope, we're going to go up even more because I can't get my pens. Okay? They found that that limit came out to be that number. Okay? And they said, well, that's just going to be our exponential growth number. Hey, great, more power to them. And it caught up. Okay? So let's graph this number. So this function, e to the x. So f of x here is going to equal e to the x power. Okay? Yesterday we said that we wanted our exponent to be 0, right? Okay? So that's going to go. So that means the first point that I'm going to put on there, if my x is 0, what is my outcome? What's the value of my function when x is 0? 1, because e to the 0 power, anything to the 0 power is 1. So that's going to go through the point 0, comma 1. Love it. Okay? Then we said yesterday we want our exponent to be equal to 1. Okay? Well, if I put 1 into that function, I get e, right? So that's going to be e, which is approximately 2.71828. So if I go over 1, now I'm up here. Okay? So this function to me looks like it starts over here and then it grows like that. Would we agree with that? So yesterday we said something about maybe, well, there's a y-intercept to this function. Where's the y-intercept for this function? 0, comma 1. Okay. Yesterday we said something about a horizontal asymptote. Okay. Now, e is a positive number. Okay. It's a base of 2.71. So yesterday we learned that that should be a growth function because b is bigger than 1. Well, it is a growth function. Yes, love it. Okay. Yesterday we said our horizontal asymptote was the line y equals 0 because I can put any value of x into that function and it's never going to be 0 and it's never going to be negative. So that would still hold here and have a horizontal asymptote of y equals 0. Okay. Good? Okay. Those two rules, you want your exponent to be equal to 0 and your exponent to be equal to 1. We want those two rules still today. Okay? Later on, we're going to be able to maybe kind of just say, well, one of them, yes. The other one, maybe. Okay? And I'll show you that in a minute. Okay? So we have that. Okay? So, yesterday, we said that if b was greater than 1, it was a growth function. And if b was between 0 and 1, it was a decay function. Well, with e, because the base, e, is always bigger than 1, how can we make these be a decay function? Okay? That's what the question that we're looking for. I want to get this to be a decay function. Okay? So what we're going to do is we are going to experiment with some graphs. Okay? So my first graph that I'm going to put on here, and I think it shows up in blue, is that one that we just graphed. So that's our parent function. Okay? Y equals, or f of x equals e to the x. Okay? So now what we're going to look at is we're going to look at this k number up in here. Okay? And we're going to tweak that k number to figure out maybe that will make it be a decay or not. So give me a value of k. 3. Okay, so 3 to the x. Okay? Now, logically speaking, thinking about this in logical fashion, should this still be a growth, or do you think it might be a decay? Okay, we're just guessing here right now because we probably remember from Algebra 2, but we're just guessing, still thinking it's a growth. I would still think it's a growth. Do you think it's going to grow faster or slower than blue? Faster? Okay, all right, well, let's see. Oh, yeah, grew a little faster. Okay, made a much more sharper curve. Still went through the point 0, 1. Okay, I like that. Okay, went fast. Let's come up with a different one. Give me a different one. E to the half. Okay, still positive. 0.5x power. So, do we think it's going to be a growth or a decay? Decay is our guess, okay? Do we think it's going to decay slower or at the same rate as blue? Or faster than blue? Slower? Okay, well, let's see. Okay, I think this one comes up in black. Oh! What happened? It's still a growth. Okay? That's why it still makes it a growth, right? Okay? Well, so we're trying to figure out how to make it a decay. Because that's our function, right? Why, right now our function is a times e to the kx power. Okay? So how can I exponentially make that happen? Make it a negative. So let's try e to the negative x. Tab first, then e to the negative x. Oh, Nelly! I think we found it. Right? Because now that's a decay. Because it's getting smaller as we're going to the right. And let's put up two more. Let's put up negative 4x. So do we think that this is going to decay faster or slower than now pink? Faster? Okay. Decays a little faster. Let's put up negative 0.5x. So now this would be faster or slower than pink? Slower. There it goes. Notice how all of those, now see, now this, I got all these funky things. Let's get over here and let's go f sub 1, then we had f sub 2, then we had f sub 3. This is riveting right now for those people that get to watch this from the didn't get to class today because of the attendance, or the assembly, I should say. Yeah, that's pretty. That is just pretty. That's so pretty. Let's screen capture that one. And then we're going to go here, back to here, and then now we're going to go. Oh wait, tap the brakes. I got to go this way first. Yeah, but. Yeah. All right. So let's put that all together. What makes it be a growth? K is positive. If K is greater than 0, we have a growth function. It's going to look like that. Okay? What makes it be a decay? K is less than 0. Makes it be a decay. All right. All right. So let's compare yesterday to today. Okay. These are the two general forms of exponential growth and decay functions. So yesterday we said that that function was a growth function under what condition? Which was greater than 1? B, did you say? Yeah? Okay, that's what I thought you said. I thought you said if B was greater than 1, it was a growth. Okay? And yesterday was a decay if what? So if B was between 0 and 1. Yep. Okay, greater than 0 but less than 1. Then it was a growth. And that's great, but that's a lot of stuff to remember because it's like, oh, is that a growth? Is that a decay? It's still positive, but okay. Today, it makes it a little bit easier because today, if K is greater than 0, it's a growth. And if K is less than 0, it's a decay. Okay. So putting it in different words, just so, oh, that's a different color. That's a horse of a different color. Name that movie. Anybody? Good job. Wizard of Oz was that movie, by the way. Okay. 1939's greatest hit. Okay. If my exponential function is of yesterday's form, then the growth rate is controlled by the value of b. If b is bigger than 1, then the function has exponential growth. And if b is between 0 and 1, then the exponential function is a decay. Now, you may be saying to yourself, why is Linz making us rewrite that down? We literally just said that. And here's why. Because in word form, when you see it written out in words, this next part, you'll see why E is so much nicer. Okay? If my exponential function is of the form a equals e to the kx power, then the rate of growth or decay is controlled by the value of k. If k is positive, it grows. And if k is negative, it decays. Okay? So it's a much cleaner. These two sentences are saying exactly the same thing. It's just one is yesterday when you got a lot more rules to follow, and one is today where it's if k is positive, it grows. If k is negative, it decays. Okay? So, different way of saying the exact same thing. All right, let's graph some. Okay? So, sketching exponential growth and decay functions are a little bit difficult because e is an irrational number. It's not nice. Okay? It doesn't make very good, easy math. But this is where I said we can do one of those and then not necessarily the other one. Okay? So if I'm looking here at f of x equals 4 times e to the 0.5x, okay? I want my exponent to be 0 yet. Okay? I want that y-intercept. I want that, exponent to be 0 in this case. So I'm going to plug in 0 to find my. Plugging 0 in here does two things for me. One, it finds me my y-intercept. And two, it's the easy one to plug in. Okay? So 0.5 times 0 is 0. E to the 0 power is 1 times 4 is 4. Okay? So this goes through the point 0, comma 4. Okay? Now, yesterday we then said, now we want to get that exponent equal to 1. Okay? Right? And so in this case, what value would I use to get my exponent equal to 1? 2. I'd use 2 here. Okay? 0.5 times 2. 0.5 times 2. 1. Okay? E to the first power. Well, that's that 2.7 number, right? So it's a little bit less than 3. Right? Times 4 is going to make it be like a little bit less than 12, though, right? Okay? So I'm going to say in that 11.5-ish range. Okay? Can I borrow this for a second? If I actually calculate what 4 times e to the first power is, it actually is 10.87. So it's in that range. Okay? We're not looking for exact here, okay? Because if we wanted exact, we would, we would put graph paper and grids on and all that stuff. So, but it's way over here and it's way up here. Okay? So does that make sense that it's growing? Actually, be a little higher than that. Because this is 4, so then that's 8, so then that's 12, so it'd be way up here. Be up in there somewhere. Okay? So this is growing like that. Do we still have a horizontal asymptote? Yeah. What is it? Y equals 0, because I didn't have anything after this function in this general range over here. I didn't have anything over there to shift that function up or down. So it stays at y equals 0, and my y-intercept is the point 0, 4. Okay? What I'd like you to do now is I would like you to graph this one. Okay? So graphing this one. For those of you watching this at home, you should pause the video here and graph that one on your own. Did you pause it yet? All right, so 0, I think, is a good one to put in. Don't you agree? Negative 2 times 0. 0. E to the 0 power. 1 times 14. 14. Plus 1. 15. So that tells me a couple of things just by doing that math. I have that extra part after the exponential part. So that does what to my whole graph? Shifts it up, right? So I've got my my horizontal asymptote is shifted up 1. So now my horizontal asymptote is up 1. I go through the point 0, 15. I'm going to put that way up there. Okay? Is this a growth or a decay? The decay, because k is negative. Okay? So here's how I go about doing this math, because I'm a little bit different than most people. Okay? So I'm going to put in 1 there. Okay? Just so I can see where it goes. Negative 2 times 1 is negative 2. E to the negative 2 power is like 3 to the negative 2 power. Right? So that's 1/9. 1/9 times 14 is 1.5-ish. Okay? Plus 1 is 2.5-ish. Okay? Love the ishes. Okay? So this one comes down quite rapidly. Which makes sense because that negative 2 allows it to decay faster. We talked about that when we were graphing all those different ones. Okay? That's all I got for you today. Hope you have a good Friday and hope you have a good weekend. I will tell you this, that there are some videos that are posted on It's Learning. If you're still a little confused about this exponentials and log type stuff, or need some synapses to refire, or if you're doubling up and you haven't gone through this part yet in Algebra 2, okay, then you should watch those videos this weekend so you're ready to go for next week.